Hello, I'm Brent Ursenbach here with Mark LaLiberte from Construction Instruction. Today we're going to talk about moisture management in our homes. Mark, we've had other discussions, and they all lead to at least a component of moisture in our home. We build a home for comfort. We keep the water off our head with a roof, and we have walls and such. But as we've talked in the past, we create moisture inside our house, and of course we have moisture trying to enter our house from outside.
Correct.
So let's talk about moisture management.
It's a great, it's a really important strategy because I think it is the most detrimental thing to our buildings, yet it's one of the most fundamental things to life, right? How many of us look out, especially someone who lives in the desert, I love when it rains. I want to see it rain and go, not, uh-oh, I'm going to have a leak in my window. I want to be really happy with that. So if I look at all the ways in which water affects us, it comes in different forms in the way it affects buildings, right? So rainwater really just falls on the roof, and if I can shingle it off, shade it off, eave it, get it in gutters and collect it, I can remove the rainwater, preferably off the roof. That's then directed away. I then have the rainwater that hits the cladding, maybe in a windstorm, or adds to the cladding. As the cladding gets wet, and then it creates a different flow. So this is the liquid water portion. So now the liquid water can go against the foundation, down push against the soil, creating hydrostatic soil pressure, and pushing against the foundation. So these are all the life cycle of rain. But we have a lot of other functions with moisture. And we put building materials that support the capillary rise of water as well. So if we look at that, first there's the big liquid water, that's the big one, It can leak in an outlet box that was stuck to the outside, a poorly detailed penetration in the roof around a chimney cap. So that's all the places water can leak in. Now we look at the other three sources, and basically it's capillary rise. So we'll take a piece of wood and set it too close to the ground. Water can get sucked up the end of that and cause it to fail. And we can wick water in wood well in excess of hundreds of feet because we've got trees to prove that. And then we have concrete and masonry that absorb water in excess of 1,000 feet. And so as we look at all the forces of moisture on the building, we have to look at it and say, where is it starting? What material am I going to put in it? And what risk is that material? Should it be more durable, or should it be able to manage those conditions? So moisture is a pretty complex thing. And then in the inside, we talked a little bit previously about how the moisture inside the building wants to get out, and that's called diffusion. It's the ability for more water molecules inside than there are outside, which means it's trying to find a way to push on the building. So all of these forces simultaneously, unfortunately, are happening at the same time. And so the last piece is the air leakage component. So as the air leaks back and forth, it also carries with it an armload of moisture. So breaking down moisture in its fundamentals, we'll first start with liquid water, and we can build on that. But liquid water is just flashing, and that's part of the moisture game, flashing around penetrations, weather barriers, very careful articulation of installing windows. Do windows leak? And we'd say, yeah, they'll probably leak. We know roof windows leak, so we just don't put them in, Windows get in an opening, and so now we've learned to slope the pan flashing into the window, caulk it from the inside so the water that does get in can always drain out. So we're trying to create a house that's forgiving enough to take on the weather, but understanding that it has to get rid of it quickly, because the water that resides is the water that fails, right?
Okay, so looking at, I started in construction 50 years ago this month.
Right, wow.
And I've seen a big change in the way we build homes.
Right.
My first home was a rectangle.
Yeah, exactly.
A little ranch rambler rectangle. Everything we see today has multiple claddings, pop-outs, cantilevers,
It's crazy.
all kinds of stuff on
Right.
it. So I guess each one of those creates another path for moisture into the building.
Yes.
Because you have all these dissimilar materials.
It's a great observation, Brent, because if you think about a house that has a square roof or even a hipped roof, at least I know where it's being concentrated, and I've really divided up the amount of moisture. I look at roof lines that there's 10 and 15 roof lines. One of them's tilted over here, another one comes down over here, and it dumps all of its water into one spot, sometimes over the front door, right? But if we look at those concentrations of water and the complexity of the house, I also have recently seen a lot of cantilevered windows, or recessed windows is what we like to call them, of course. So they're recessed back into the house because the architecture community likes this kind of depth of look. So I'm going to put the window, let's put it another 6 or 7 inches inside the house. Like, well, that's not a good idea unless we create this fairly elaborate system for flashing and drainage back to the outside slopes. If we look at other countries, the Europeans have done a beautiful job of putting a slope like that. Well, we don't like that. We want the 2 slopes that sit flat so that we could set a plant on it, I think. I'm not sure we want to do that, but appreciating gravity and that everything flows out. So the more complex the roof, Bilbao is a great example of that in the Smithsonian, in the Guggenheim. That roof is incredibly complex and it leaks. So if we have complex roofs, the effort and art of making them leak-free matters. The installation of windows, complexity of that, more complexity adds a more intense need to do a better job than, like you said, the house of past. And if I could have a nice 3-foot overhang, there's a data that shows that a house that with a simple roof, with a good overhang, sees very little water problems. Imagine that. What a concept. And so now when I substantially change all of that and make it much more complicated, I have to make and commit to the same level of accuracy to manage those functions as well, to say, well, wait a minute, this wall, this exposure is going to have a lot more risk. Now let's put in better layers, better flashing, and really spend time there. What if I spend another hour there today really flashing it well instead of the smack, smack, smack it up, put it in and put some siding over the top? I better go back and say, can this stand the test of time? And that's a critical function.
The overhang thing, of course, with the HVAC in the back of my mind all the time, I loved overhangs because they gave us shading on our windows.
Exactly.
Okay, so we have all these things that you're talking about. I see multiple different building papers on the outside.
Correct.
And as I understand it, some are different than others. Can you kind of explain what we call weather barriers?
Yeah, that's a good question. I see a lot of variation. There's probably 30 to 50 types of weather barriers on the market. And in some cases, we've said that anything that looks like a sheet good can be a weather barrier. Some of them punched holes in them, some of them a sheet of black paper tacked on the wall like we did for a long time, but it can no longer act as its base function. So let's kind of define what we want them to do. I want it to keep out liquid water. I want it to keep out air because air is part of its function. If air blows by, the potential for water to blow by is there. But should some moisture get in that cavity, some in the outside, I'd like it to be at least ability to dry through the product. So those are kind of those functions: keep out water, keep out air, but be some level of drying. Then it's the application of the product. There's 3 different functions of weather barriers. There's one called a mechanically attached, which is stapled on. There's one called a peel and stick, which has got a backing to it. You peel it off and you stick it on. It's got its own adhesive to it. And there's one called fluid applied. And those are actually come out of a 5-gallon pail, and we can roll those on the building and make them monolithic with the sheathing. So those are all 3 types. All of them can be very successful and functional. Of course, there's a cost with each one, right? As you go from the mechanically attached to the peel and stick to the fluid applied, costs go up quite substantially. But all of them need care and attention. Just because I put on one type doesn't relieve me from having to be very careful with the details. So I'm building a house now, and I used all of them. And looking at how careful you had to be to watch negative laps, where sometimes it would get the opposite direction. I want to make sure I'm tucking my rain pants outside of my boots, not into them, and my raincoat not into my pants, but outside. I want to make sure that shingle flashing and layering is still an important component. So should a tape or sealant fail, I've got that as my backup, belt and suspenders. So whether you put a product on the market, I'd always look for a brand that has a good series of adhesives and tapes that match its product. So if I'm going to use a fluid applied, I want to use the fluid applied company that has other systems that attach to it. Do caulks work with that product? If I'm going to use this nail-on flashing, does this tape stick to that one? Does your tape stick to my tape? Does my caulk and sealant stick to your product? So what happens is we go, I got some of that, I'll grab some of that, maybe we'll pull some of that, and I got something in my truck. When we put that together, a lack of compatibility creates a problem. So there's a lot of pieces here that have to go into deciding what do I want to do to protect my building from weather. And that's pick a system, pick an approach, train a crew. You wouldn't like to have a plumber come in here and install plumbing? No, I'll figure it out. I don't want that, right? We've all seen people actually do that. But if I know how to train and install, bring in a manufacturer's representative, can you come and train my crews? Imagine how critical water management is and how much effort and time I should spend to teach my crews, hire a professional, get it right, and then, as you had said earlier, inspect it. Inspecting a blower door is just one of many inspections. Have somebody come around, does this look watertight? Building inspector is not supposed to check the weather barrier for accuracy, but somebody should make sure it's tight.
Okay, very good. So with that water management, I've heard you talk, and we've talked in the past about our very common building product, OSB,
Yep.
which doesn't do well in water, but we've also talked quite a bit about, kind of tying into another discussion, the condensation that forms on the backside of OSB on the inside, the inside facing surface.
Right.
Same thing happens on roofs.
Right.
So how do we prevent that condensation, that water from condensing on the underside of roof sheathing and on the inside of walls?
It's a great question. And, I think it's all part of what we've sort of been building up to at this stage is that, condensation and airflow is the contribution of moisture into cavities and into attics that we don't usually see, because the OSB is usually outside of our purview. Once I've installed it, I'm not sure what's happening to it. It's acting as my structural sheathing. It's acting as kind of sort of a nail base for my cladding systems, but I don't know what happens to it until later on. And what we do know is that if moisture is allowed to go past my claddings, and I believe that all claddings leak, siding, stucco, brick, all claddings leak. So if the water gets past the cladding and lays on the weather barrier, runs off at the bottom, I'm good. As long as the OSB stays dry, it's a remarkable product, right? OSB can hold up for centuries if it was kept dry. There's probably a little debate in that, but for a long time. But if I look at the fact that if the water gets past the weather barrier and lays on the OSB, now it begins to absorb the moisture like it's supposed to. It's wood, it's supposed to do that. It then starts to delaminate the wood, right? It kind of even changes the structure, it expands and swells the OSB, breaks the glue bond and begins the failure cycle. That's outside driven. If I go to the inside, and we talked about moisture on my windows, remember we said that if condensation's on my windows, it could be happening somewhere else. So if I have air leakage around an outlet box, air leakage into a cavity, that moisture that I've generated in your humidifier, thank you, that you installed in my house is now going to sneak its way out and then find in the wintertime a cold sheathing. So dew point is the driving force here in that conditions. So let's say I've got a 40% relative humidity in my house in the middle of December, and I'm generating moisture, family's over, we're cooking dinner, and I just keep raising that moisture level. And the amount of air leaving the building is enough to find that sheathing and condense on it, because it is a low permeability product. If I'm going to buy a sheathing made out of glue and resin and stuck together, I don't want it to have a high permeability level. And so by the nature of glued resin, it's not going to allow that. So the moisture hits the sheathing and begins to condense because it's cold. The whole wall in front of it all has been insulated. It hits the sheathing and begins to condense. Now it's absorbing the moisture, starts the failure process. An entire winter cycle could be enough to cause some pretty bad damage if I'm not managing that. So again, our testament to tight buildings is I don't want this moisture in that wall in the wintertime. So how do I manage that? Well, either quit breathing or seal the hole. So all of those things, we can build buildings out of potentially challenging materials as long as we appreciate what's the material that I'm using. It's lower cost, although not today, but if I'm using OSB as my sheathing, it's a little bit lower cost. What's its risk? And you're like, don't let it get wet. Don't let it stand in the way of moisture transfer, and it'll hold up beautifully. It'll be strong and solid. So you have to put systems on the inside to prevent airflow to the cavity, systems on the outside to prevent rain and water and snow from getting in contact with it. If I keep the product isolated from moisture, it holds up quite well. And we didn't discuss the last piece of that, but where the OSB kind of sits by the ground, I oftentimes see people take the OSB and they finish it really close to the grade line. So when it snows and piles up, the moisture gets sucked up at the bottom too. So appreciate the product, what it can do, and for sure appreciate what it can't do and wasn't expected to do. And design our buildings around managing that level of moisture within the building.
Okay, and then, so continuous insulation on the outside is part of one possible solution,
Yeah.
or spraying foam, close-cell foam on the inside
It can help.
can help because it keeps the dew point.
Yeah, and I think that when we look at exterior insulation, whether it's on the roof or on the walls, we start realizing that if I could warm up that OSB, remember it's going to be hopefully now above the dew point and it doesn't condense there. I still have to be equally careful with the outside rain, the outside water, flashing beautifully, but the thermal insulation does a couple other, probably more important things, and that's to interrupt the conductive flow of the framing of energy. So I take out an insulated wall, put some insulation on the outside, the whole system warms up. Your calculations for heating and cooling goes, oh my, insulation on the outside changes the thermal performance of that wall. I can right size this equipment a little better. So now I have my blower door data. I pulled the sticker off the window, that's accurate. Now I know what my wall performance is going to be, and it's been enhanced. Let's get to work and really pick a system for this house. So all of those pieces you can see are additive to improve building performance, longevity, customer satisfaction. Those all win if they're played together.
Great. One last question. So we talked about stopping the moisture from getting into the wall. I see homes all the time. They come in, they put a visqueen plastic material for a vapor barrier on the inside.
Right.
They don't do anything to the electrical boxes. And soon as they might seal it around there, but not the wire penetrations, but as soon as the drywall contractor comes in, he takes a router and he cuts a hole around in the vapor barrier around every single box. Correct. So are vapor barriers doing any good? Or should we be addressing it elsewhere, making sure the house is slightly negative? I mean,
it's a very good question, Brent. And I think that the math is pretty clear. Vapor barriers, especially in a climate like this, really don't perform a very good function in that building, because I'm putting it up there with the understanding that trying to manage vapor transfer across the wall, that'd be the process of diffusion, moisture molecules moving through the gypsum, getting to the plastic and getting stopped. That process is remarkably slow. The problem that we have is the outlet boxes and sealing it, and so I would rather put my drywall on, put a coat of base primer, a PVA on the wall, and get that as my vapor control layer, so I have a little bit of control. But more importantly are on the outlet boxes. And they do make products nowadays that are vapor diodes, basically. They can put up a material on the wall that if the moisture content in the wall goes up, the vapor content, so vapor pressure increases in the wall cavity, it actually can turn around and increase its permeability and let it dry back to the inside. So there's these products. The Europeans have done a beautiful job of designing this idea of vapor diode vapor barriers. And so I'm now putting up a barrier on the inside to act as an air barrier, not purely as a vapor control layer. So now you'll see people taping the joints and seams and being very meticulous with that product. I would suggest that in this climate, people are extraordinarily careful as to whether they install a sheet of visqueen or a sheet of polyethylene on the inside surface. And if they do, it better be near perfect. And I think that that's a high risk, because now I have to make sure the outside water management is perfect, because a little drip in the wall means it's not driving the other way. It's not going to dry to the inside. The longevity of risk can be significant. So I would say vapor barriers probably don't provide the function that we thought they did, because we aren't installing them the way they would have to be.
Very good. Well, thanks, Mark. I really appreciate that.
Thanks so much. Such a pleasure.